So now we move on to the modeling the environment. So that's what we have been working on this on. This is called DTU balancing tool chain. We have been developing this for quite some time now. So now I move away from hybrid a bit and rather model the larger European energy system. What does that mean? So what are the basics of balance, right? Sure. Utility only for PV battery. That's a good question, and we are discussing that in IEA task as well, that should PV plus battery or wind plus battery be considered as hybrid. Typical consensus is wind plus battery and PV plus battery are also hybrid. The maps are for utility scale, so I believe there would be PV plus battery as well, but when we are talking about utility scale, these are hundreds of megawatt scale, so we probably are not looking into few of the smaller PV plus battery and wind plus battery. These are all definitely renewable hybrids, so we definitely have discounted wind diesel, which has been there for many years, and there are also few wind hydro and things which are also missing at this. It's not so easy to develop these maps because not enough amount of information available, and we have a standing request from Wind Europe if we can always update their maps. So what is the basics of balancing is that the electricity production must always match the demand, and that's also because storage is neither economical at large scale and nor logical as well, that if you can generate the electricity as it is required by the demand, then you should do that, right? But at the same time, the dynamics are evolving. So we are seeing that variable renewable energy are increasing all around the world. So what we have been seeing all around the world until now is that we have a load pattern, and generations, they being dispatchable, they were following the load. And now probably we're going into a shift that generations are getting less and less dispatchable. It's based on the nature, and we should move into the uh, phase where loads and or consumption should try to follow that. And that's where the flexible consumption, be it hydrogen production, be it battery storage, be it any other demand side response, and all those things are coming into the play. Right? This is the change in the dynamics at the same of the power system. At the same time, there is a change in the market dynamics as well. That majority of the VRE are being transacted in the day-ahead market today around the world, and then the gate are being closed 12 to 36 hours. And then the challenge is that until now, if you have only 5%, 10% renewable, you could live with it because you have a forecast one day before and you are fine with it. Even it has a forecast error, you could live with the reserves. But when you have 80% renewables and that has a huge forecast error in the day ahead, you cannot live with that planning altogether. So you have to move closer to the time of operation. So the new markets need to be evolved. And even there where intraday market, balancing market, they are getting much, much more prominent. And we also saw that in the Europe due to the gas crisis because of the Ukraine war, that the balancing prices were getting unreasonably high. And the regulators have to come in and cap the balancing prices, which we don't want in an open market, right? The regulators coming in capping the prices. So we until now we had the day ahead market, then we are moving towards we are having intraday market now, where the gate is closed 1 hour before, and then the balancing market, which is also trying to move more closer to the real time. So that is getting close in the Europe, and I'll come into more details later, into up to the 25 minutes. And then comes the real time control and the physical delivery. And the real time control is the last aspect where um, you have the opportunity to again um, reduce your mismatch with the forecast. And then comes the settlement, which is the pricing settlement the day after. So we'll start with the Danish system, and this is by design a bit outdated because this is what Denmark has been doing until now. And I think from this year, 2024, there's a new uh, market instrument has come up, or market platform has come up called Mari, and I'll come into details later, which is trying to harmonize the balance between all the European countries. And some countries have subscribed to it now, and some will come do it in the coming years. And but it is in a way following the Danish principle, in my opinion, to a large extent. There are differences, but I still use this for education purpose because it helps quite a lot in understanding the basic fundamental behind how to mitigate the forecast error. So in the day ahead market, so independent power producers, they get the day ahead prognosis of the renewable plants, what they can generate. Based on that, all the independent producers, they go and bid in the day ahead market, where the gate is closing 1 day before at 12. So we develop the market model to do that. And then there is an intraday market, which is until the 1 hour before. And until lately, this intraday market was utilized for something else. Like you have promised something in the day ahead market, but a large power plant has gone down and you cannot provide that power anymore. So you open that up in the intraday market for someone else to come in. But with larger penetration of renewable coming in, or larger share of renewable coming in, now this is also an opportunity for the independent power producers to say that, yeah, 1 day before I had this much forecast error, but now my forecast error has improved. And this is still debatable whether it's useful to proact 6 hours before or 12 hours before, because it is also driven by the forecast models. And the forecast model, and Matthew knows much more than I do here, they are having two components. One is the meteorological model and another is the data model, right? The data model you can use for short-term forecast, whereas the meteorological model, which are based on reanalysis data, and you update them, and they are very computationally expensive, and you update them maybe 6 hours or 12 hours before. And then what is the point of how much should you rely on the old meteorological reanalysis data, or how much you should rely more on the data-driven models, which are closer to the uh, with the improvement in the machine learning model and whatnot, closer to the operation. So that's the debate there. That if you want to work more in the intraday market, you rely on not so accurate meteorological models because you don't have the updated data until 6 hours before. So 12 hours before, you might have a not so good model and you might go act and you might lose money in the market. But then comes the regulating power or the balancing market, which is the 1 hour before. And this is what Energynet used to do until now, and Simba was their tool, but they were also using other tools, BID and whatnot. In future, it's gonna be muddy. That they now see that what has been bid in the market and what is my 1 hour ahead prognosis in terms of renewables forecast 1 hour before, and I can calculate my imbalance, and then I can, instead of a market, I have a list, a merit order. I know which is the cheapest generator with this capability, which can provide within 1 hour my power. I can call them and they can provide me in that way, I can get much more reserves, which are offline now, come into online, and they are cheaper. So they can be coming from gas, they can be coming from hydro or some small CHPs, DCHPs, they are cheaper. If I don't do that, then I go into the real-time balancing, or even hour ahead forecast has some error, which has to be taken care by real-time balancing. And real-time balancing has to taken care by the automatic reserves. And until now, the automatic reserves has been quite expensive because you had to connect fiber optics to each of the generators and send an automatic signal. And this is quite expensive. But then again, another question is coming up towards future. All these small demands, electric vehicles, if we can connect them through internet and if they can be reliable, maybe they can become cheaper than a gas turbine or a CHP, which I need to acquire from the regulating power. So we don't know in future how it would be, but it would be a balance between automatic and manual reserve. But this is what we need to model in order to know how much imbalances are happening and which kind of resources are being employed. And the thing is that I'll come to that later. We need to do it for future. Why we need to do it from future? Now I connect back to my system, which is hybrid. And if I want to invest into a hybrid power plant today, which is going to operate for 25 years or 30 years in the future, I need to know what would be the balancing requirement in 2030, 2040, so that I can invest accordingly. If I should go in this kind of setup, should I go in the spot market? Should I go into the intraday market? Should I go into the balancing markets? Should I do more real-time balancing? This will let me know what kind of assets should I put, because storage is still quite expensive and quite depreciating asset. And it's not like a thermal generator or gas turbine. You can put it there, it does not depreciate over years. And you don't care, okay, for 30 years, it will generate me revenue. If I don't see that until 2030, the balancing prices are going up, I will not install a battery today. I will rather install it in 2030. But I will get the grid permit today with my capacity requirement for the battery in 2030, because I will not get that in 2030 for sure. So there is quite a lot of game to be played there, and quite a lot of considerations need to be taken with risk associated. Do you have any question here? And also, please let me know. I cannot improve my voice, but I can speak a bit slower if it's very difficult to understand me. We move on. Until now, the whole power system has been defined and designed so that the reserves are used to handle large disturbances and contingencies. We just kept signal, right? Suddenly a generator goes down, suddenly a load goes down. For example, in continental Europe, it's designed with it n-1 contingency. That means at any time, it should be able to be resilient and secured and stable even when one of the component goes down. And it has been observed that there is a large line in France which connects to two nuclear power plant, each of 1500 megawatt. And if that line goes down, then at any point 3000 megawatt can go down. That is the biggest contingency in continental Europe, or it's also dimensional fault. So we have designed the reserves accordingly that we should be able to handle 33,000 megawatt at any point of time. National Grid in UK, they go even beyond and they go to N-2 contingency. The reason being that it's an isolated islanded system and they need a bit more higher risk. So whenever a disturbance happens, the frequency goes down. Like here we are missing generation, a large generator has gone down. So the frequency starts going down. As a result, the first line of action is some automatic reserves, which are called frequency containment reserves in Europe. In US, it's called primary reserve. I think in India and many other countries, it's also called primary reserve. So as the name suggests, frequency containment reserve. The aim is to contain the frequency going down to a very low value or very high value. However, it does not bring the frequency back to the initial value, that's the 50 hertz. So the next reserve which comes into the play is called frequency restoration reserve. So frequency restoration reserve has two responsibilities. First thing is to bring the frequency back to 50 hertz, and the second thing is to replenish the already activated frequency containment reserve. So you can see now the frequency containment reserve, which was already activated, they has come down to zero again. The reason being that now, if there is a subsequent fault, the frequency containment reserve is again available to help out with that fault. And the next thing comes is the replacement reserve. As the name suggests, it just replaces the frequency restoration reserve because the frequency was already at 50 hertz. So there is no frequency. It's not called frequency reserve, but it's called replacement reserve, which just replaces the frequency restoration reserve already active. But this is for a disturbance. But if there is a slow variation due to forecast error, what does it mean? That we had forecasted that wind will be blowing at 15 meter per second, but it was blowing at 8 meter per second. And then we are missing certain amount of power. Yes.
Just a question. The first one is on the meaning of frequency, and the second one is what is the typical time scale of the frequency reserve. Wow.
Okay. So yeah, what is the frequency is that it's a very basic concept in any AC power system. But like you say, that it's the number of cycles of the AC current, of course, but it's also the synchronous speed, synchronous electrical speed at which all the synchronous machines in the power systems are rotating. So in order to maintain the security or stability in a power system, we would like to contain the frequency within a very strict band, and that's the quality of frequency or the quality of the power system. So as close as you can maintain with the within, like for example, in Europe, 50 hertz. So as close you are able to maintain it within the 50 hertz, more stable and secure your power system is. And it's a global signal. So you measure it in a synchronous power system. So you measure it in Switzerland, in Germany, and in Italy. Anywhere you measure it, it's the same signal you get. What's the typical time scale of frequency restoration RAM? It depends from power system to power system. it's more stringent. You go to a smaller power system and an isolated power system. In continental Europe, it's I think it needs to be activated within 30 seconds, and it has to be activated. No, sorry, it's activated within 15 minutes, and then you stayed until an hour or a bit beyond until the replacement reserves are coming up. And the 15-minute is decided because the frequency containment is they are required to be activated within 30 seconds, and they are asked to be activated for 15 minutes. So that means you should bring up the frequency restoration reserve by 15 minutes to relieve the frequency containment reserve. And those requirements are a bit stringent in Nordic power system and Baltic power system and Ireland, UK. Same would be, I don't know about French, but how it is done, the LFC, but I would like to understand and learn more later. Yeah, so as you see, there is a slow variation due to forecast error here. So that means the frequency would not be going that much down to activate the frequency containment reserve. Rather, it would activate the frequency restoration reserve because the frequency did not go down that much, but you still want to restore it back to 50 Hz. And then the regulating power comes in relieving the LFC or the AFRR, automatic frequency restoration reserve. So see here, we don't call it replacement reserve because it is not replacing, it is not designed to replace the frequency disturbance mismatch. But we have been calling it regulating power, but more and more this is getting harmonized. And in coming times, they are all replacement reserve because they are replacing the AFR. So what we want to do is to activate proactively this regulating power to reduce this LFC driven AFR, because this is the whole principle. Because if you are operating with 80% renewable penetration, and if all of your frequency restoration reserves is being used by the forecast error of the renewables, then the contingency happens. Then you are in a major risk because you don't have that reserve available anymore to help you during the fault, right? And then we'll go into blackouts and whatnot. So we want to prevent that. So what do? Either you dimension separately what reserve you need for mitigating the forecast error, or you have strategic reserve or this dynamic is or dynamic acquisition of reserves, or you ask the generators themselves to mitigate the forecast error by whatever way they have, instead of you being the system operator being responsible for that. And there are different methods employed all around the world to do those things differently. So now what we see that in the previous one, there was a slow variation due to forecast error, but we did not proactively activate any balancing reserves, balancing power. So as a result, the LFC was activated. But now, if we can manually activate this regulating power based on my forecast error, that one, then what we see, so we assume that we have a perfect hour ahead plan or perfect hour ahead forecast. Then there is no dent in the frequency. Nothing is activated based on the automatic reserve, and it is all handled with the regulating power or the manual reserve. So based on this principle, we have developed something called balancing tool chain amplitude. So what we do, is we have the energy system scenario, which tells us that in 2030, in 2030, 2040, how would the energy system look like? Means how much renewables will be installed, where they will be installed, how big will be the hub height, how big will be the rotor diameter, how much energy will be generated by the renewables, but also be doing a system level optimization, investment optimization. We know how much of other kind of generators will be there, how much, and this is also policy driven. How much of the nuclear will be there in France? How much of the nuclear will be there in Sweden? How much of the CHPs will be there? How much of the electric vehicles will be there? How much of the thermal will be there in UK? How much of the thermal will be there in Germany? How much, what kind of interconnections will be there between different countries based on different reports, different projections, and the optimization that, and then we run the power flow to find out how much will be generation each hour in the whole. So that the energy system scenario tells us the how the scenario would look like in 2030, let's assume. And then we have our internal tool called CoreRes, which will generate time series for variable renewable energy, wind and solar. And then we can model the day ahead market, or we call it the spot market, which can model the how the each hour in the day ahead market, which will be the generators will be generating or dispatched, and how much of the, what would be the cost of energy, what would be and the CO2 emissions, spot prices, whatnot. And then we model the balancing market, like we showed here. And then we find out what is the upregulation reserve requirement, down regulation reserve requirement, and balancing cost. And finally, we also model the area and the frequency control, which is the in the real-time operation, that in the real time, how much is the forecast error and how much we have activated in the balancing market and how much imbalance is in the real time and how it will impact the, or how much we need to dimension the frequency restoration reserve and containment reserve, and what would the frequency quality in the future. So do we have any question now?
Yes, sure. One question.
No, it's not a rule of thumb. That's the part of our chain that we get the answer. How much do we need the reserve? So it's kind of a tuning, right? So if you have zero reserve, your frequency quality is deteriorating. So you start increasing the reserve until the frequency quality is up to the mark as it is today. So that's how we estimate and quantify how much reserve is required in the future, both for balancing market and for the automatic reserve. What we don't have today is a feedback loop into the energy system scenario. What we don't say that in your model, because this is a very complex model that you are working with certain assumptions. Sometimes it might happen that I don't have enough reserves in the system itself to activate, right? So how do I get that reserve? So now we are starting a PhD. The advertisement would come up again and soon again, where we do this looping, that the balancing market model and the area and frequency control model will feed back to the system, energy system scenario, and tell them that you need to consider this in your scenario modeling. Otherwise, during operational planning, I do not have enough resources. But we do not have a rule of thumb, but more of a systematic methodology to quantify. And I will come to that in the presentation later.